is one of the, I guess, if you don't mind my saying, one of the chief people on the Mu2e experiment. And I believe this is the first Mu2e talk we've ever had here. You can correct me if I'm wrong. At least the time I can remember. So Dave actually started working on CDF way back when, I guess, with Roy Schwitters at Harvard. And then he went on to become to CERN as a CERN fellow, worked on LEP, and actually worked on measuring the B branching fraction of the Z. So then he went to LBL, and you've been at Berkeley for quite a number of years.
Close to 18.
18 years.
Inventor of the jet probability tagging algorithm. It lives on.
At CDF?
No, it was ported to CDF, though, from left.
From Alan. It started in Alan, went to CDF.
Oh, so you two were on Alice together?
We overlapped both experiments. I'm sorry I didn't get a chance to say
You were in your office hours.
yeah, it's midterm, day after tomorrow.
Well, you can go out to dinner with us afterwards.
I don't know about dinner.
So anyway, we can talk about
Little
it.
kids.
Yeah, you have that problem. Not that it's a big problem. So then,
No, they're a problem.
well, then you worked on Babar for a number of years, working on Babar, and so since the proposal stage all the way through the final little beam that came in.
We're still on the bar.
So, well, I know people are still analyzing the data from that, and in fact, will be for several years. And he's been on Mu2e for 4 years, and basically his group at LBL is working on the tracker electronics, and which actually, when you see this talk, you realize how important those are. So, without further ado, Dave.
Okay, well, thank you for that nice introduction, and thank you for inviting me here. I'm very happy to tell you about Mu2e, both Mu2e conversion and the Mu2e experiment. So I'm going to go through a very brief historical
stick, I think.
Yep. Historical summary of lepton flavor as concerns muons mostly. I'll talk about what Mu2e conversion is, since that's something that's not very common, at least not yet. I'll talk about the Mu2e experiment, talk about what performance we expect to get from that experiment, the schedule and status, and conclusion. So lepton flavor, I think of as being the status of lepton flavor, I think is well summarized by a quote from I.I. Rabi back in the 50s, which was, who ordered that? And it was in reference to the discovery of the muon. Muon was discovered in cosmic ray cloud chamber pictures, like this one on the right here, almost at the same time by Anderson and Street. This is a picture of a particle penetrating through a half-inch thick platinum sheet. Can you imagine telling your funding agency you wanted a half-inch of platinum to do your experiment? But that's how they did it. And by analyzing these tracks, it was determined that this had a mass somewhere between the electron and the proton, which were the only particles known at that time. And so it was considered to be a middle or meson particle. The immediate suspicion was that this was, in fact, the realization of Yukawa's prediction that there should be some condensate of the strong nuclear force that holds the nucleus together. But in fact, further study shows that this meson was not strongly absorbed by the nucleus the way that a Yukawa meson would have to be. And in addition, eventually, soon afterwards, the pi meson, the actual Yukawa particle, was discovered and was found to decay sequentially into the muon, which became now the muon as a distinct particle from, say, a pi or a pi meson. So as soon as it was discovered, people asked, okay, so what is this particle? It seems to behave somewhat like a heavy electron. Maybe it's an excited electron. Maybe electrons have substructure just like atoms have substructure, and we would expect it to decay radially down to the lower mass state. And in fact, starting right after its discovery and understanding, people started to look for decay Mu2e gamma, and it was not seen. So it became clear that this was some new kind of particle, hence Rabi's comment. And what that basically means is there was no prediction for there to be a muon. It doesn't seem to serve any function within the understanding of particle physics that existed at that time. And so if we move on to the modern understanding of leptons in general, muons in specific in the standard model. So we know from these nice summary charts here, there are 3 generations of fermions where the muons, the charged muon and its neutrino, form an electroweak doublet, the left-handed version of those, and the right-handed massive muon is an electroweak singlet. Lepton flavor is strictly conserved, and in the actual literal standard model, the neutrinos are massless. The Higgs mechanism, we now know, provides the charged fermions with their masses. And this was beautifully demonstrated recently in the measurement here, this is from Atlas, of the Higgs to tau-tau branching ratio. Well, it's a rate as a function of mass, and what we see is a very small excess on top of this very large standard model background from Z to tau-tau of a signal that's consistent with the branching ratio one would expect if the Higgs coupled the tau-tau with the strength that would be necessary to give it the mass of the tau. So this is very nice. However, this is a rather descriptive model. I mean, I've heard this chart here referred to as the periodic table of particle physics. I think people have heard that expression, and it's actually not anything close to that. The periodic table of elements is a chart that shows how structure can be explained by underlying properties, right? We can build atoms out of protons, neutrons, and electrons and understand how they array in this nice geometric form, whereas this is just description. We don't know why there are 3 generations. There's nothing in this model that predicts it. We don't know why the masses are the values that they are. Okay, we can say that the Higgs gives them their mass, but that's just shuffling a mass constant into an unknown coupling constant, neither of which can be predicted. We don't know what really connects the 3 generations between the leptons and the quarks. While the cosmologists like to talk about the baryon asymmetry of the universe, since that's what they look at through their telescopes, I actually think a more acute problem is what's the origin of the lepton asymmetry of the universe, right? There's no net charge in the universe, so for every one of those protons out there in stars, there has to be an electron somewhere. And we have no idea what generated those electrons separate from the positrons that should have been pairing with them. In fact, from the work we did on the bar, studying CP violation, and in other places, we know that the charge, the CP violation component of the matter asymmetry cannot be explained purely in the quark sector. So in fact, it might be even a more pertinent question to ask, what's the lepton asymmetry origin? And then to be a little bit provocative, you can also claim that the problem with the standard model is that it's wrong. And by wrong, I mean it doesn't describe phenomena that we've actually observed. For instance, this is a nice measurement that was made in the 90s by Super K showing that atmospheric neutrinos, so neutrinos coming from muons that decay in the atmosphere, disappear. There are fewer of them as you look for farther and farther distances that they have to travel as a function of their proper time, in effect, compared to the electron neutrinos. And a more even evocative picture coming from Camland, where they looked at electron neutrinos from reactors and found that the electron antineutrinos would disappear, reappear, and then redisappear as a function of the proper time, showing an oscillatory pattern that we understand now to be due to mass oscillations. So the fact that the flavor eigenstates are not the mass eigenstates of the neutrino. The neutrinos have to have mass, and because they have different mass, there's a beat pattern between their mass wave propagation that allows you to extract at some distance in time away from their origin point a different flavor of neutrino depending on where you started. So neutrinos have mass, but we really don't know why. We don't know what mechanism generates that mass. The fact that they have mass means that the neutrino, the right-handed neutrino, has to exist, but we don't know if that's its own particle or whether it's, in fact, just the anti-left-handed neutrino. And that's a rich field to understand, which people are actively pursuing, and it's great stuff. But it also opens up a lot of interesting questions about charged leptons. Since we know now that lepton flavor is not conserved, there's nothing in the standard model that actually says mu has to stay a mu. It could have changed into an electron if there was any possible process. And so we know that the standard model is incomplete. it becomes interesting to look again into Robbie's original question. So to phrase it again, what is it that stops a muon from decaying into an electron and a photon? Absolutely nothing. There's no fundamental process that's violated by this. So any mechanism that couples the generations indirectly or directly should allow mu to e gamma. And the fact that we don't see it is an interesting hint, or it could say that this is an open field whereby we might be making the next discovery that could start to explain why there are generations at all. And in fact, the fact that neutrinos oscillate implies that there has to be a standard model process by which muons can decay into electrons and photons. It's this loop diagram here where the W first emits the mu neutrino, it oscillates, and then recombines with the electron neutrino on the other side. This process is unobservably small. It's got a predicted branching ratio of order 10 to the minus 54, and you can understand easily why it's so small. It's because the time that this virtual W is allowed to exist as a very massive particle is much shorter than the characteristic timescale on which neutrinos oscillate, which is on the order of kilometers, kilometer 100 MeV. So what this says is that we've got a very clean playing field in which to look for new phenomenon. Any observation of this charged lepton flavor violation, be it in mu to e gamma or some other process, would be definitive proof of some sort of new physics and hopefully give us some insight as to what's going on in the overall structure of the flavor sector.
Are you going to talk about the typical predicted branching ratios in SUSY?
I'll say a little bit about that.
Okay.
I'm not going to give any numbers. Most of the numbers are old because they haven't been updated for constraints from the LHC.
From the fact that we haven't found Susie.
They keep squeezing the limits, and
I hate it when
they
that
haven't been
happens.
propagated into this.
Well, the thing,
sector.
obviously what we want to see is if Mu2e could push the bounds on SUSY on the leptons anyway, way beyond what LHC could do. That's
Yeah.
a question that's hovering in my head.
So I'll get to that in an indirect way, but ask again if you don't feel I've covered it. So I just want to point out that there are a couple of outstanding anomalies that we haven't fully understood that are connected to muons and might also be indicators that there's something interesting going on. The one everyone is probably familiar with is the G-2 magnetic moment measurement made by the Brookhaven E21 experiment, which showed about a 3.5 sigma discrepancy with theory, depending on which exact theory you believe in. That's an experiment that has engendered enough interest that it's going to get repeated at Fermilab in the next few years. There's also a very recent measurement of the hydrogen charge radius, which was done with muonic hydrogen. So this is a spectroscopy measurement where essentially you measure the Lamb shift and interpret the Lamb shift as a radius, a physical size. And when you compare the radius made with muonic atoms, where the electron has been replaced by a muon, with the electron version of that, or direct measurements of the charged proton radius with electron scattering, you find about a 7 sigma discrepancy. So maybe something going on there connected to the muon. I'm showing a picture of their experimental apparatus used in this measurement just to indicate that further on it has some reminiscence to the Mu2e apparatus too, which I was amused by.
Question, sorry, this is maybe more a theory question, so you can duck it if you want, but is the hydrogen charge radius thing, is it sensitive to radiative corrections at the same sort of level that the muon magnetic moment is? Do you know anything?
They're different.
About that?
They're not. This is not. Doesn't have large hadronic and light by light type contributions. I've only vaguely scanned the theory papers on this subject, so I can't be claim any expertise. But it is a topic of conversation. Okay, so let me talk about Mu2e conversion, and I'm going to start with the process whereby muons are captured on atoms. So if you have a negative muon, it quickly, if it's at rest, it will quickly fall into the lowest S wave state of the atom. That's the most energetically favorable because the muon is so much heavier. than the electron. In fact, in the case of a muon dropping onto an aluminum atom, you've got about actually 700 keV of energy that gets dissipated in the form of X-rays. So it falls, it's that much lighter than the normal aluminum atom, if you will. Once it's been captured, there's several things that can happen. The muon can decay, the way we know muons already decay when in free space by emitting an electron and 2 neutrinos. It does it in a slightly modified way because it's actually recoiling this decay against the nucleus. That's a part of the system now. It's no longer a 3-body decay, it's a 4-body decay. In the case of muonic aluminum, this is happening about 39% of the time. But in addition, the muon can get captured onto the nucleus. The muon orbit, the Bohr radius, is comparable in size to the actual size of the nucleus. And so it has a very large wave function overlap with the nucleus compared to, say, for instance, to the electron, which is orders of magnitude further out in orbit. And that gives it a strong chance to undergo inverse beta decay, which results in transmutation of the element and creates, in this case, an unstable nucleus. The magnesium-27 that's produced is too neutron-rich to be stable, and it wants to spit out neutrons, and it also can spit out protons and photons. This actually is the dominant process by which muons cease to exist when they're in a bound state with heavy elements. And in the case of aluminum, the additional branching fraction, if you will, into this capture mode reduces the lifetime from the free lifetime of 2.2 microseconds down to 800 nanoseconds. So Mu2e conversion is actually a combined process that includes the nucleus. It's a coherent conversion of the muon into an electron in the field of the nucleus. So that field of the nucleus serves two purposes. One is that it provides possible interaction probabilities through capture-type phenomena that would not exist for a muon in free space. And the second is that it provides recoil. So if the muon is tightly bound to the aluminum, when it does convert, the recoil is against the atom mass, which means that the electron is emitted with essentially the entire rest energy of the muon. It gives you a very good experimental signature. You have an isolated monoenergetic electron coming out of a stopped piece of material. There's a little bit of energy loss due to the electromagnetic binding of the muon into this potential well, and in the case of aluminum, it comes out to be about 105 MeV electron. And in terms of discussing the experimental quantity, we normalize the observation of Mu2e conversion to the capture cross-section, not the decay, because as you change atoms, the fraction of decay versus capture changes, and it turns out you have a more stable ratio if you reference the capture. So that's just a definition. There's no physics in that. So getting to John's question, so there are other processes beyond the standard model that would mitigate or perform Mu2e conversion. There are two basic types. One is loop terms, which are the SUSY ones. So for instance, you could have a neutralino-slepton loop where the sleptons mix. And this produces, the predictions have been in the order of 10 to the minus 12 level for the Mu2e conversion. So pretty close to the existing limits. But I think when you apply the LHC limits, those get a little bit tighter. But they're well within range of what we expect to see with the Mu2e. You can also have exotic models with, say, additional Higgs doublets that can, again, through loop diagrams, transmute from muons to electrons. There's a second set of terms which directly involve interactions with the quark. For instance, some sort of an anomalous Z or a leptoquark theory where the muon and the quark are actually combined at some lower structure level. These are processes that can only be accessed through Mu2e conversion. These loop diagrams, this photon in the case of Mu2e conversion is a virtual photon, but you could also have muon decay into Mu2e gamma that would be sensitive to exactly the same process. So because there's these two basic kinds of processes with no specific model that we favor, the theorists have come up with an effective Lagrangian, which has two parameters, one of which describes the ratio between the loop and contact type terms, and the other is the mass scale. So it gives you an overall scale dimension to the problem. You know this was defined by a theorist because going from loop to contact, if you wanted full loop or full contact, is a scale going from 0 to infinity. Whereas an experimentalist would have chosen maybe 0 to 1. I guess theorists are more comfortable working with infinities than experimentalists. So.
Just in that upper left diagram, maybe this is a question for the theorist. Does that have to be a second neutralino, or can that be in a loop? That would be a chi0 2. I mean, so that
No, that would normally be the LSP.
that would normally be the LSP.
Just a general comment is that in SUSE you're definitely probing completely different parameters in this than in the direct SUSE searches. You could have a signal in any combination in one or the other. They're really completely complementary. So you could have no signal at LHC, a big signal here, vice versa. All those combinations are a priori allowed. So they're testing different things.
I have to say the literature is very sparse on this subject and out of date. Most of the papers date from the
And if you make a very
2007.
specific model, they can be related in this. But I mean, in general, in the MSSM, the point is that the LHC is just not sensitive to flavor violating parameters, and these things are proportional to flavor violating parameters. And so they could certainly be as big as your experimental bound given existing LHC limits, and even if those limits increase. So I'm just saying, it's all good. It's motivated independently of what they see at the LHC.
And suppose you had maximal mixing between U tilde and E tilde. I
Then you
assume
need-
that the LHC would
Then
put
you
some
need
bounds
squarks
on
of
the
100
masses.
TeV. If you have maximal mixing, it's something like 10 to 100 TeV squarks, which you'll never find at the LHC or even a 100 TeV collider. So even with a 100 TeV collider not finding supersymmetry, this is still well motivated. So,
That's good to hear. I
Yeah.
mean, that's, certainly we believe that there's a lot of experimental
yeah.
sensitivity, theoretical sensitivity here. It's just the literature seems a bit out of date.
Yeah.
So let me move on. So let me go to the experimental side of things. So there are previous measurements of this, and I'm going to give a little history in the next slide. This is the most sensitive existing measurement from 1996. This was an experiment done at PSI with their beautiful muon beam there. This is a search for Mu2e conversion. You're looking for, as I mentioned, this monoenergetic electron. In their case, they're measuring a momentum in a spectrometer. What you're seeing is a lot of background in this figure from their paper. There's backgrounds coming from the beam that created the muons. There's backgrounds coming from cosmic rays. And there's a background coming from these decay in orbits. This is an irreducible physics background. When the muon is captured on an atom, as I mentioned, it can just decay. And there's a small tail of the Michel spectrum in this mitigated system where there's a coupling with the atom that can extend all the way out to the kinematic limit, although with great reduction. Their measurement, they did measurements both with titanium and gold. Their titanium measurement is actually more sensitive, but it's never been published. So no one ever quotes it as an official limit. They do have a published result on gold, which is the current world best measurement. And if I combine on one plot as a function of some poorly defined sensitivity, all of the relevant muon charged lepton flavor violating measurements that have been made, starting with Mu2e gamma, which was made very soon after the understanding that this wasn't a new leptonic type particle, you can see that the progress has been sort of following a Moore's law, maybe with a break here in 1980, but we're already getting down to levels that are quite sensitive to new physics. The most recent, if you will, most sensitive current measurement is not the Mu2e conversion measurement, but the Mu2e gamma decay measured by MEG. They published last year, a branching ratio of 5.7, 10 to the minus 13. There are also measurements being done and proposed at PSI of Mu2e electrons. So now I'm going to start talking about Mu2e experiment.
I'm sorry, can you go back to this one? So the two lowest versions, the one on the left.
Yes,
is
these are the
syndrome
syndrome.
two. It's the same.
Yeah.
Okay.
So what we hope to add to this plot in 2020 is a point down here, or actually we hope to find a make a discovery, but if all we get is a limit, that's where we would sit. Our goal is 6 to the minus 17 sensitivity at 90% confidence, which is roughly a 10 to the 4th improvement over existing measurements. MEG, of course, is planning upgrades, which have been approved, actually, and in the meantime, they may well advance their measurement, but it still isn't much closer to what we hope to achieve. I'm going to talk more about how we hope to achieve this 10 to the 4th sensitivity. That's really the main point of this talk. If you're going to make exceptional claims, you have to have exceptional proof, and so I'll try to convince you that it can, in fact, be done. It's a bit misleading to display the sensitivity on this rate chart, because what the rate means in Mu2e conversion is different from what it means in Mu2e gamma decay. A more unbiased way of comparing experiments would be to look at their sensitivity in terms of this effective Lagrangian. So the important point here is that going from 0 to infinity, Mu2e is sensitive over the entire range of kappa, independent of model, essentially, whereas the Mu2e gamma experiments are only sensitive to these dipole, these loop diagram type terms. But even in the range where Mu2e gamma competes with Mu2e conversion, we still will see a substantial increase in sensitivity. We hope if we can achieve the sensitivity 6 10 to the minus 17th, we'll have sensitivity to mass scales up to 10 to the 4th, TeV. So this is a very deep probe in a very narrow area that we hope will yield some complementary results, say, to what we can see at the LHC.
So the blue dashed is an upgrade.
That's
on
an
what
upgrade.
you're
I'll
talking
say
about.
something at the very end. It's a factor of 10. So this is the Muni Collaboration, of whom there are about 130 of us, of which about half show up in this picture. This is the Fermilab ionized atrium, in case people have never seen it before. So the concept of the Mu2e experiment is that we're going to produce muons at the Tavotron, well, at the Fermilab complex, by hitting protons against a fixed target, and the protons interact with the nucleus. If they're energetic enough, produce a lot of pions. Those pions decay into muons, and we're going to collect and stop the low momentum muons. We need about 10 to the 18th of them to achieve the kind of sensitivities that we're hoping for. With those stopped muons, we will look for electrons coming out of their stopping point and measure the momentum of that electron as accurately as we possibly can, with the goal of seeing a conversion signature as a monoenergetic line. Now, there are 3 principal experimental challenges to this. Well, they're all essentially background related. So what we're looking for is to keep ourselves as a statistics limited experiment. We want to be a signal limited experiment, not a background limited experiment, which means we have to do better than one event over the 3-year run that we plan. There are 3 categories we have to work on. One are the beam backgrounds, and we handle these by a unique timing structure, a pulsed beam with good extinction. I'll explain what that means. We have to worry about these decay and orbit backgrounds. The way to get around those is to have a very precise momentum resolution. We're trying for 1 per mil, so less than 1 MeV on a 100 MeV electron. And finally, we have cosmic ray backgrounds, which means because we're a surface experiment, we're going to need active shielding. So this is a sort of all-in-one overview of the Mu2e experiment. Protons come in from a new beamline that's being built now, or will be built in the next few months at Fermilab. Pieces of it are already in place. The protons hit a tungsten target that sits in the center of a very powerful solenoid, superconducting solenoid here, producing lots of secondary particles. Some fraction of those are low enough energy to move backwards. We only care about the backwards going particles because we want low momentum muons. We also have a gradient field here which helps increase our acceptance. I'll say a little bit more about that. These low momentum particles travel through a curved solenoid. This is a very unusual beam delivery system where they are brought to a target of aluminum where they are allowed to stop. The ones that stop, we sit and wait for them to decay, and we look at the electrons that come out in this large detector solenoid here. The whole scale is about 14 meters. At the very back end, there's a beam stop, which keeps the beam that doesn't stop in the target from flashing back in and overwhelming our detector with background. It's also got a tiny little pinhole in the back that allows us to look for the X-rays coming out of the muons when they cascade down onto the atoms, and that's how we do our rate normalization. I can tell you more about those details.
What is the muon momentum? Did you tell us?
The muon momentum, I'll show you a picture. So the beam is an important part of this experiment. It's not like some disentangled part that you can talk about the same way you could maybe at a collider experiment. This is really part of the experiment, so I'm going to go into it in some detail. So we start with protons in the booster. That's the active element of the Fermilab complex at the moment. The booster is the ring. If you've ever been in the high-rise and sat in the cafeteria, you can see it just out past the balcony. And we need to get over to the Mu2e experiment here, and it's done through a very circuitous route using existing beamlines and one new beamline. The booster protons are brought over to the recycler ring, where essentially they make one turn, come back into what we're now calling the delivery ring. In the Tevatron era, this was part of the antiproton complex. It was the antiproton debuncher. In fact, it's kind of interesting. What limits the current we can put onto the Mu2e target right now is the fact that this antiproton accumulator debuncher was set on the surface with very little shielding on it because the currents would be so low from antiprotons that you never have to worry about it. Well, even the losses in collimators and from extraction on the septum, we get enough what's called sky shine, which is where these particles shoot up into the air and interact with particles and gas of the air and emit particles into the high-rise. They were at the point where those radiation were beyond the allowable DOE limits. So we actually had to redesign the experiment at one point to reduce.
Cover on it?
Yeah. We went through lots of options about how you could put it in a sarcophagus.
Occupancy limits on seats.
Around people's hamburgers.
It turned really ugly really fast. It was never intended to be a shielded operation. So we use resonant extraction to get beam out of the delivery ring and send it on to a new beamline M4, M5 at the new Muon campus, which we share with G-2, which will run before us. We are not compatible in running with G-2. So the beam timing is an important part of how we achieve our experimental goals. We are using 2 out of the 20 available booster batches. We operate concurrently with NOVA. NOVA takes most of those batches, but they can't use all of them, at least not all the time. They want to stack their beam and then extract it. During their stacking and extraction process, we can steal the bunches. We steal 2 out of the 8 available. That's as much as we can handle because of the sky shine problem. We spread them out so that we're active over a period of about half a second. And during that period, we rebunch the beam into a large sequence of small micro bunches, as we call them, 250,000 in this half a second period, where the timing structure looks like a very narrow proton peak, repeated again and again, and eventually muons down at the detector some time delay later. I'll talk more about this in a minute. So it's an interesting issue that the detector is live for about a microsecond. We're open to anything that can happen. It's like a dark matter type search in that sense, that we can't gate the way you could at NOVA or at LBNE. So we have to have a tight control over this kind of timing if we're going to avoid the problems from the background. So when the muons make it down to the target, we have to wait around. There's 2 reasons we have to wait. One is that there's a huge flash of beam with beam electrons and muons that are too energetic to stop coming through the detector, inundating it with hits. We have to wait for that. That's about 300 nanoseconds. But even beyond that, we've also produced a lot of pions, and we need to wait for those pions to decay away because they are actually a signal background. They're a background to the conversion process. So we start counting our clock about 700 nanoseconds after the proton pulse hits the detector, hits the target, and makes it over to the stopping target, and we're live for, like I said, a microsecond. Okay, so I'm going to talk about the beam backgrounds because all this timing stuff is relevant to the beam backgrounds. These 8 GeV protons produce a lot of junk in addition to the muons that we want, and in particular they can produce antiprotons, which is rather nasty. But the pi minuses are also a problem. There's no way we can do particle species selection of these energies. There's a very wide spectrum of momenta and energies coming out, so there's not enough handle there. The problem is that these negative particles, the antiprotons and the pi minuses, can capture on our stopping target just like our muons. And when they do, they can emit photons. This is a spectrum for pi minus capture on magnesium, which is the only thing that's in the literature. It's very similar. It's one line, 1Z over from aluminum. And what you see is that this photon that's emitted when the magnesium converts into sodium and stabilizes itself by emitting the extra energy of the pion mass includes energies right where we are going to be looking for Mu2e conversion. These photons can convert either in material or internally, and when those conversions are asymmetric, the energy ends up in the electron minus, the E minus, and that's lying right in our signal window. So we absolutely cannot tolerate any pi minuses when the detector is live. The rate for this kind of process is at the level of 10 to the minus 6. So way, way, way more prevalent than we can tolerate if we're trying for 10 to the minus 16. The antiprotons, fortunately, are highly ionizing. They're even a bigger problem, but we can get rid of them by putting an absorber in the beam, which costs us some flux, but we have to deal with that. So the trick with the pi minuses is that we just have to wait them out. Their lifetime, even with the reduced muon lifetime because of the capture process, is still a factor of 30 smaller than the muons. And in 700 nanoseconds, we get about a 10 to the 11th suppression factor of those. And when you multiply these two numbers together is how you get to the sensitivity thresholds that we hope to get. But if you think back to this picture here of the timing, there's something I haven't told you. This concept of waiting out the pions presumes that there are no protons once you've reached the end of the bunch, right? If there are any late arriving protons, those late arriving protons can produce late pions, which will then make it into our timing signal window and will be a fundamental physics background. So what we mean by extinction is we need to suppress those out-of-time protons. And that's done in a couple of ways. One is during the bunch formation in the delivery ring. There's a very fancy phase-space rotation, which I am not at all qualified to describe in detail, but it makes a nice picture where the different bunches from the booster are recombined into a single bunch in the delivery ring, and you end up with this very interesting shaped beam profile as a function of time, but it all sits within 200 nanoseconds. If I showed it on a log plot, you could see that there's nothing out here beyond 200 nanoseconds. But that's not enough. We need the 10 to the minus 11 type projection factor, and we do that with an active component. We have a dipole that lives in the delivery path, and we've tuned it in phase with the beam with a large swing. What that dipole does is, by putting in a little wiggle, this 3.8 megahertz, we essentially zero the field at the time when the core of the beam is coming through. But anything that's coming late or early gets deflected, either high or low, and then we put collimators in the beam to get rid of those. So we basically change timing into angle displacement and can get rid of it with collimation. This gives us, we believe, a factor of 10 to the minus 7, and then you add them up, you multiply them, you get the factor that we need. Now, of course, we can't rely on calculations to make sure we're not going to have backgrounds. We have to measure this in situ. We have an extinction monitor system. It's essentially a pinhole camera. It points back to the target, the stopping target. Sorry, the proton target is over here, just off the screen. We got this very narrow channel that allows us to momentum select particles and track them to measure their rate. This is using technology borrowed from Atlas, from their inner D layer for pixels, and from the readout. And we believe we can use this system to measure the extinction to the 10 to the minus 10 level in an hour. So we don't need it instantaneously with each bunch. We just need to know that integrated over our run, we've achieved this level of extinction. Okay, so one of the cooler features of Mu2e is this solenoidal transport. It's very different from the usual beam optic, dipole, quadrupole type strong focusing we're used to, but it works quite well for these low energy processes. We start off in this proton production solenoid with a large field, 4.5 Tesla. It's graded, which makes a magnetic mirror, which brings the low momentum particles forward. Those get transported through this curved solenoid and into the detector region here, which also has a small section of gradient. There we go. So I'm going to go through those in order. The production solenoid is actually the most technologically challenging. It's a very high field, and it's in a very high radiation and heat environment. All the 40 kilowatts of energy that we're putting onto this target have to go somewhere, and it's in a vacuum, so it radiates out. It has to be shielded with this very large bronze shield, and it turns out that the critical component is not the temperature that this shield, this is a water-cooled shield, that this shield has to absorb to make sure that the magnet doesn't go above superconducting temperature. It's actually the displacement of the atoms by neutrons coming out of the target. We calculate that in a year, 10 to the minus 5 of the aluminum substrate atoms in the coil that we wind the magnet with will actually get displaced. They'll get kicked out of their lattice position. And that induces enough resistance that this matrix, which serves the function of quench protection, I don't know how many people are familiar with how superconducting magnets work, but you have to have an alternate current path beyond the superconducting one in case that the temperature goes above superconducting. Otherwise, it will vaporize if you ever go above that temperature. At any rate, this resistivity of the aluminum goes up high enough that it no longer serves that function. And basically, it's not a showstopper. It just means we have to warm up the magnet once a year to let those atoms find their place in the crystal lattice once again. We actually have samples, 10% samples, so kilometer-long pieces of cable that have now met specifications. In fact, all of this cable necessary to wind all 3 of the solenoids has now passed the specifications test, and we're in the final design phases of the solenoids. The target, by the way, is this tungsten rod sitting here. At the moment, it's air-cooled design. It just hangs off of wires, keeps things simple. If it's air-cooled, it reduces the mass that the protons might interact with. And the only issue is that it gets very hot, and it means we have to keep a good vacuum in that area to keep it from oxidizing.
Is the power the same as the booster power?
No, well, yes. I mean, per one of those bunches, yes. That's right.
Per bunch.
So how does that 5/1000th number compare to, I don't know, some other muon production?
It's high compared to the LHC for the CMS solenoid, for instance. Yeah, it's quite a bit higher. We're quite a bit closer to the point where the neutrons are produced, and there's quite a bit of it. Right? Usually, don't you put a superconductor right around the production target? Okay, so this cool S-shaped solenoid that's sort of the signature feature of Mu2e was actually first proposed for an experiment that never ran at the Moscow accelerator. The point is that the particles, when they execute a helical trajectory, follow the field lines. And as long as you contain those field lines inside the solenoid, they'll go wherever you point it. Now, there's a really cool second-order effect, which is that by having this bend in here, you necessarily have a gradient in the field across the horizontal plane. That horizontal plane, coupled with the longitudinal motion of the particles, gives a vertical displacement, if you remember your triple product fingers. And what that does is it allows us to separate out the charges and the momentums. So we actually have an asymmetric collimator that sits in the middle here that stops all the positives and lets the negatives through. And it also, by the diameter of this collimator, defines the momentum that we select. This is reversible, by the way. We have calibration modes where we need to rotate and look at positives. And so there's a little gear wheel on this. This is all in vacuum. It drove the engineers crazy.
What's the scale on this? Can we use
this is about 5 meters from here to here. Yeah, so this is a huge collimator. It's not a small device. And what's also cool is that by reversing the bend, this vertical displacement comes back, so our beam is nicely centered when it comes back into the detector. So the detector solenoid is, by some sense, the most conventional of all of these. It's large in the sense of it's long, it's 6 meters long, but it's no competitor CMS in terms of the total stored magnetic energy. This is kind of a lousy picture here. There's a gradient region in the entrance part, which serves as a magnetic mirror for the electrons. So when the muons decay, the electron is produced isotropically. In order to increase our acceptance, we bounce them back and send them towards the detector. There's some shielding in here which protects the detector against protons. There's actually a very small gradient in this quote-unquote constant field region just to sweep out low momentum particles, keep things from spiraling infinitely. That was a problem on the MEGA experiment, brought them down. So this stopping target, this is answering your question, is very thin sheets of aluminum. At the moment, 17 of them. They're suspended on wires to keep the mass outside of the active beam region as small as possible. The thickness, the total mass of this target is a compromise between stopping and straggling. Stopping, we want as much material as we can to stop as many muons as we can. But once the muon has stopped and is decayed, we want as little material as possible in front of that electron so that we can measure its momentum as precisely as possible. What we end up with is a momentum spectrum of stopped muons that peaks at about 30 MeV and craps out at about 50. We can't see anything beyond that. And these are just lost that go through the detector and radiate and produce backgrounds. But we get about 10 to the 5th of these for each one of these 1.7 microsecond cycles. And that's how we build up over the years, the 10 to the 18th that we need. So the key active element of the Mu2e experiment is this low mass straw tracker. It consists of sort of like MWPC stations that have been built out of straws. Each one of these sort of trapezoid regions is a double layer arrangement of close packed straws. We have a big hole through the middle of the detector where there is no instrumentation. That's to allow the beam to flash through, but it's also because the most common source of electrons is going to be these decay in orbit, and they're mostly limited by half the muon mass in momentum. That's as much energy as they can get in the normal Michel decay that doesn't recoil against the nucleus. So we let those go through the center of the detector and keep our rates down. One of the interesting features of this is that it has a curved manifold. I don't know very many detectors that have to deal with this issue, and we've recently come up with a solution that works and is cost effective. Namely, we're going to make the curved manifolds that hold the straws and keep the gas seal in out of 3D printing. There's some sintered materials that are radiation tolerant and quite low outgassing, and it looks like it's going to be a perfect solution for what we need to do.
Don't straws have a lot of material in the straw?
Well, we have very thin straws, 15 micron. Let me hand this around. 15 micron wall straws. This is them. They have a very thin gold and aluminum layer on them. They're fragile, but not impossibly fragile. And they actually have quite good tensile properties. You can pull on these
Get that right
things.
through?
You can, don't just destroy them willfully, but yeah, you can pull on them. They're not going to break. It's actually one of the critical technological developments that we've pushed the manufacturers down to these very thin layers. We believe we can even go lower. This isn't the limit. But for our purposes, it's enough.
Curved?
No, they're straight. They're held at tension. To build this device, to keep them from gravitationally sagging, we have to pull the straws and the wires. Both are pulled.
Basically little balloons.
They are little balloons because they're operating in vacuum. The whole cryostat system is in vacuum, so these guys have to hold an atmosphere of pressure too. And we've been actively doing leak testing and tension testing and stretching exercises. I can tell you about it if you want. Total, we see an electron going through this sees about 1% of the radiation length, which is what we need to achieve the kinds of resolutions we want. The other interesting thing about this is that we have a novel readout with both ends of the straw being read out. both ends instrumented with a very precise TDC that measures the delta time down to the sort of 100 picosecond, which allows us to place the hit along the straw to a few centimeters. And that turns out to be really critical in the pattern recognition.
I guess I'm surprised it didn't go with a design more like the CDF jet chamber. Or,
With the sheets.
yeah.
We looked into a wire chamber design. It was proposed by that Italian
Not,
group.
well, not the DTX, but the
The problem is the end plates.
the COT.
The problem is the end plates, John. You need a lot of mass.
To hold,
To
the
hold
tension
it.
on the wire.
The end plates. You can actually
Well,
solve the inner
wires
cylinder.
could run the way your straws would run, couldn't they?
You
have
still
a
end up
wire
having to have
on the
a.
outside.
But that's what I thought about the DTX.
You end up with this design if you
I'm
do
sure you
that.
thought about it.
Yeah, there is an option to make it out of a more standard drift chamber with a hole in the middle, but it turns out to be more massive. That was a quite clever design. It was running at 0.4 atmospheres chamber with very high-tech components, but you just can't get around those endplates. Even making them out of carbon fiber and all sorts of different materials, you just can't beat the material down. Okay, so a second detector we have is a calorimeter. It's, I think, unique. I'm not sure if it's 100% new, but it's unusual in the sense that it has hexagonal crystals, which allow us to get a better close pack factor for this circular cross-section we have to reach. It's divided into two pieces, both of which have a hole through the middle, again, to let the DIO electrons through. And there's a half-wave separation between them, so the electrons from the muon have a sort of characteristic pitch angle after they've been rotated in the magnetic field with solenoid gradient. And we space these two disks out by a half a wavelength, and that gives us a very good acceptance. So if one doesn't see it, the other one does, even if it does go through the hole. We're still discussing whether it's going to be a LISO or a barium fluoride crystals, although the barium fluoride is cheaper and it's probably going to win. But the goal of this detector is not to measure the energy, is to measure timing and to provide particle ID, which becomes important. It may also be the source of a track pattern recognition seed, but at the moment we believe we can seed internally to the tracker. Cosmic rays are a big problem. We have a laughable overburden. I'm sure anyone who's doing underground experiments would shudder to think about working under 10-meter water equivalent. So we have a very large flux. The detector is live, so 30% of the clock roll time. We have a lot of backgrounds to reject here. And the muons are real background potential. This is a simulation example where a muon sneaks in through our solenoid, loses enough energy bouncing off a collimator that it spirals in right through the target, so it would be coming from exactly the space we expect it to be, and makes it into our detector looking just like an electron. Of course, it's a muon, so when it hits the calorimeter, we're going to be able to tell the difference. But still, if you calculate through how many you expect to see, there's quite a few of them, and some of these are going to decay into electrons and give you something that looks just like the signal. So we actually need an active veto system if we're going to beat this 10 to the 3 background down. So what we do is we just cover everything with scintillators. These are scintillator strip chambers with an optic fiber readout. We have 4 layers in order to do 3 out of 4 coincidence. We need that in order to keep the efficiency high. There are a lot of neutrons flying through this region of the detector, and the neutrons can induce fakes. And if we want to keep the detector live any reasonable fraction of the time, we need 3 out of 4. We calculate we can achieve a 99.99% rejection of incoming cosmic rays with this system. This is a test stand that was set up recently at Fermilab.
So do you end up with do you veto if you see any cosmic activity?
3 out of 4. 3 out of 4 that lines up. There's a table of patterns that we understand could lead to a muon that would be visible in the detector.
Because it seems like it's overkill just naively, because most of those
That's
things,
true.
muons won't look anything like your signal.
Right.
So do you?
This is
do
an
you just-
offline veto. It's not a hardware veto. we're going to read out everything. I'll say something about DAQ at the end. We'll go back afterwards, and if it's clear that this muon couldn't possibly have caused any problems, we can recover those points. But even with 3 out of 4, we estimate the dead time is at the few percent level. Okay, DAQ, thank you. So just to mention DAQ, because it's something I've actually done a little bit of work on and it's kind of fun. It's a triggerless architecture. We're just going to stream everything off of the detector and let computers make the decisions. We've tested that we can stream all the raw data that we expect to see coming out of mainly the tracker onto commodity components. We're going to use a gigabit Ethernet as our networking fabric. This is our event builder, essentially. Sorry, 10 gigabit Ethernet. And the track finding is what we use at the moment for our online filter, as we call it. It's actually running on an offline computer. We need a factor of 500 reduction. This is not LHC. And at a 400 hertz rate, we will be writing about a petabyte a year. So again, reasonable amounts of data, especially for people who are used to LHC type experiments. The data chain goes from the detector to a dedicated processor to a commodity server, and we've just finished an evaluation of 2 different server technologies, which surprised me, for the computer nerds in the audience. We compared the Xeon ES, which is a sort of middle-of-the-road number of cores per CPU, versus the Phi, which is the current hot object with 120 cores per CPU. And even using Intel's compiler optimized for these different environments, we found a better performance on the Xeon ES. So that's our baseline at the moment. And this meets spec, what we need in order to get the data reduction. This is running the actual algorithm.
And is there a substantial cost savings as well? Or?
There's some. There's some, yeah. We don't need, the important thing we were trying to verify wasn't even comparing these two, was to just verify that we didn't need to go to some GPU or some exotic computing architecture in order to solve this. Straight CPUs work.
Why does fewer cores give you...
These are faster.
Okay, that's per core then.
That's the total rate per box. If we have a server, one server holds, I can't remember how many, 8 CPUs, but you can either choose this or that, and this is better, even though it's got fewer cores. It's quite a large factor faster.
Yeah.
Yeah, it was very surprising to me. So, performance estimates. I'm going to have to speed up here, I'm sorry. So, muons, when they capture on this target, produce a large number of background particles. We get about 1 gigahertz of hits in the tracker during our live gate, not even counting that initial flash going through. Basically what's happening is we're getting a lot of photons, and the straw walls act as radiators. They produce Compton electrons, and those Compton electrons spiral through the magnetic field and zap the detector. This is an amalgam of 1 microsecond of lifetime, showing all the hits in the tracker. So how do we get rid of those? Well, we use the fact that these hits cluster in time and space. Here we're exploiting the 3D readout, the time division readout. We can find these low momentum electrons that are producing hundreds of hits each as a pattern in both time and space. This is the resolution we get from the time division, showing the different directions of the overlapping straws. And by using a neural net algorithm, we can reject 90% of this background, keeping 99% of the conversion hits, and then you can start to see the track that we're hoping to measure. And it's actually a non-trivial process to find this track. Again, this isn't LHC. We have no beam crossing. We have no primary vertex. We have no information at all about where this track is going to be found. We're just open for a microsecond. We have to look for everything. And that's another reason why we need the 3D space points. What we've done is used a pattern recognition algorithm based on a robust, it's sort of an image pattern recognition algorithm that we stole out of industry. And we've bolted onto that the Kalman filter fit from the bar, which has an internal simulated annealing algorithm which gets rid of the outliers. And we end up with a quite good resolution, about 100 keV intrinsic. That doesn't include the energy straggling. That's just internal to the tracker itself.
That's a 57 MeV?
This is 100, 105. 105 is our target.
For your signal.
Signal. Yeah.
So what we end up with when we put everything together into a full G4 simulation, including all the different backgrounds, The DIO background, by the way, has to be predicted from theory. There's this interaction with the nucleus that gives you this very long tail beyond the Michel edge at 57 MeV. And that is been calculated. It's a subject that probably needs to be revisited before we actually run. But what you end up with is this very fast falling. It's about delta E to the 5th power edge, whereas our conversion electron is 105 MeV. It shifts down due to energy loss in the target, and it also gets straggling due to energy loss fluctuations in the target, but it's still cleanly discernible from the primary background, which is this edge right here. The other backgrounds, the beam-related backgrounds and the cosmic rays, are flat in momentum. We'll be able to do sideband subtraction to measure those. But this one, we basically have to measure from only one side, and as it overlaps the signal region, that determines how well we're going to do.
This is the full data set simulation?
This is a 3-year
3-year.
run, which gives us a single event sensitivity to 2.5 10 to the minus 17.
So if there's no signal, you're left with just whatever can happen on the edge, right?
That's right. It's just the fluctuations. It's the tails.
Right.
We're a very tail-sensitive experiment. Yeah. So that's why we're very concerned about the reconstruction. For instance.
Must be systematic so that it get you on the edge.
Well, the energy straggling all goes negative, right? So that systematic doesn't enter. It's really a question of promoting, where we might misreconstruct, say, 2 overlapping tracks or pieces of one track with another. And we've analyzed that in simulation, and it looks manageable. As long as we can keep the background rates down.
That large angle scatter, single scatter.
Yeah, the single scatters are possible, but remember, there's a very low mass tracker. So, that last plot was a real idealization in the sense that you're sort of mapping out a PDF. There's hundreds of thousands of conversion electrons to get this smooth curve. It's normalized correctly, but it's not what you would actually see. We've run some toy experiments where we take those curves as PDFs and sample them, and what we'll actually see in a 3-year run is something more like this, where you've got tons of statistics actually to measure this decay in orbit edge falling down here, and then you get into the signal box, and if we're lucky, we'll see a handful of events. That's what we're hoping for. Now you can run an ensemble of these toy Monte Carlos, and what we find is that we expect a distribution like this for the number of conversion electrons. This is with 3 10 to the minus 16, and what we see is that 90% of the time in these toys, we end up with a 5 sigma discovery threshold, if that's what our Mu2e actually is. Now, a critical component of this measurement is that we actually need to measure the absolute momentum, right? We're going to try to distinguish this edge from these points. And John, you were talking about that in terms of the tails, but it's also just in terms of this edge not being in the right spot. So we need to calibrate the momentum of the tracker, and it's tricky in this environment. We don't have any upsilons or j psis to set a line mass with. We don't even have pi zeros. We don't have much. So we have 3 redundant methods that we're going to use. One is just dead reckoning, if you will. We're going to measure the heck out of the spectrometer pieces as we put them in. We can X-ray the tracker pieces as they're built. We've already shown we can achieve 50 micron accuracy. We'll measure the magnetic field to about 2 Gauss. And if you propagate those through, you get a statistical error, if you will, of about 20 keV. We hope that that's going to be good enough. There's also this DIO edge. That's real. We'll measure it. And if we believe the theory, we'll be able to turn that into a calibration to the momentum. So in terms of statistical error, the edge has enough statistics that we can measure that endpoint, if you will, and know the momentum scale to about 15 keV, and we're still trying to understand the theoretical errors that might be involved. But our primary method of calibration will be the in situ, where we switch the polarity of this collimator and pick out the positives. We'll have positive pions. If they stop in the target, they will produce a monoenergetic E+, unfortunately quite a bit lower in momentum than our signal, 70 MeV. So we have to run with a reduced field in order to see these. We can accumulate in about a day enough to see a clean peak with about 100 keV statistical accuracy, but then we've got systematics to fold into that still. So, status and prospects. Well, right now we're all very busy writing our TDR and getting ready for our CD2 review, which is going to occur in just a few months. But we're ready to start groundbreaking. We actually have money in the 2014 budget, and the site preparation work is going to start in just a few months. So we're actually really getting busy, and there's tons of activity going on. People are fabricating pieces, detailed designs of exactly how the target hull, the whole detector hull is going to look. This is a mock-up of the stopping target. There are measurements being made of proton stopping fractions. These are tests of conductor. This is a test of the rails. Lots of things. It's a very busy activity. And just to go to that point that was raised on the sensitivity plot I showed earlier, so we have done a study at Snowmass of what we might be able to do in the future with this same apparatus. Now, because we're only sitting at a sort of 20% duty factor, if we had a better proton source, a more continuous access to protons, we could actually achieve about a factor of 10 increased sensitivity just by putting more protons on the same device. So with very modest detector upgrades, we think we can go another order of magnitude. We can also do follow-on studies. If we do actually see Mu2e conversion in aluminum, we can move to different target materials, which gives us model sensitivity. I can say more about that if there are questions. So I'll finish since I'm very late. So I think flavor is a poorly understood aspect of the standard model, and here we are 80 years after the discovery of the muon. We're still asking basic questions about what it is, and there's still some recent results which indicate that it might be a fruitful place to look. Muon to electron conversion is a powerful new probe of new physics. It's sensitive to a lot of models, and it's complementary to the kinds of discovery potential of a hadron collider program. And Mu2e is intended to give us a big boost in sensitivity, and we're on track to having some physics in 2020. Thanks.
So questions?
If you were really only interested in the decay Mu2e gamma, is there another different experiment you could build that would give you, at the price of the contact interaction one?
Well, there's an upgrade to MEG being
But
worked
that
on right
seems
there.
like you're already beating that too, right?
MEG is, yeah, we're beating that. The hard part of Mu2e gamma is the gamma. You have to measure that photon. And they're already pushing the limit. They have a liquid xenon calorimeter with very fine-grained cells. I doubt you're going to be able to do much better than that. They don't even think they can do much better than that.
Questions? So, one question. So, what about pi minuses? When you observe pi minuses, the models to actually predict what comes out of the nucleus when you observe a pi minus, you get lots of strange things. How do you know you're not going to get electrons coming out of there?
Well, the one we've worked on is the photon, right? So this is pi minus being absorbed, producing a photon. So electrons can happen. We've modeled them in the context of internal conversions, where this photon internally converts, because you have to do something to conserve electron number. Right?
So, but can you convince me somehow that, I guess this is the question I often get. So if you saw half a dozen events, what actually are you going to do to convince me that, that this is, that
So,
you're not, you just haven't missed a very subtle background?
We have, okay, so this is not a one-dimensional measurement, right? We have the momentum spectrum. Whoops.
David,
RPCs, anything that has a higher mass scale, cosmic rays, we'll see things over here where they can't possibly be coming from conversion. So we've got a sideband that we can check. We also have timing. We also have, the timing structure that we expect in this nice clean band where we have no pions means we can go earlier and look at a region that's pion rich and study the pion capture electron background. Right there.
Didn't Syndrome actually see some events in that region? I'm trying to remember.
They had some, well, they have, depending on how they set up their cuts, but in the gold data, they removed them all with hard cuts. Yeah, so we have timing, we have momentum, and we have another variable I haven't talked about at all, which is the pitch angle, which, because of this gradient field, there's only certain processes that can end up with something that fits into our acceptance. So we can actually study that too. our goal is to end up not doing a one-dimensional fit here, but a multi-dimensional fit.
Questions?
Go back to that slide towards the end with the pi plus. Just wanted to make sure I understood the,
Oops, pi plus.
yeah. So you just reverse your fields and you can.
We don't reverse the field. We reverse this collimator. that
Reverse
does
column,
the, yeah, the field stays the same, except we have to bring it down. And we have to do two things, actually. I was a little fast on this slide. We have to reduce the field so that geometrically the electron coming out of this, the positron, has the same acceptance in the tracker. And we also have to reduce the beam intensity. And we have to run earlier, right? These pions are decaying much faster than the muons, so we have to run closer to this beam flash, which may affect the detector background rates and change the acceptance. So, but our hope is that we can study those effects in simulation and that they won't be first order. Our understanding, as we have it now, which is limited, is that those are not first order effects on the momentum scale. We're never going to be able to measure the rate or the resolution correctly this way, but we should be able to get the scale.
Okay, well, let's thank Dave again. Thank you.